In this video, we're going to go through a full comprehensive example on how to design how to select a beam member. So let's recap on the process. Step one is you select a beam size based on the bending moment. Once you choose the size based on what can handle the bending moment, the lightest member that can handle the bending moment, you then check shear and then you check deflection. And then you revise the beam if either of these don't work. Typically, the shear will work. Deflection often does not work. And then you have to choose a larger member. So here's a typical question. Choose the lightest wide flange, which is an I-beam, steel section that can support a live load of 790 pounds per linear foot and a dead load of 300 pounds per linear foot over a simple span of 18 feet. And we will use GR50 steel, which has a yield stress of F of Y equals 50 kips per square inch stress. Okay, so at this point, I assume that you guys know how to get the max shear and the max bending moment, either from the diagrams that you know how to create or the equations, the shortcut equations, which is probably what you should be using. Those are going to be faster. Okay, so you then need to take this max moment, because we're going to do moment first, and we're going to multiply this moment by 1.67 to beef it up a little bit to be able to have a stronger member, or a beefed up factor of safety. So we take our 1.67, multiply by 44145, which is right over here. And that gives us a final moment that we need to design to of 73,722 foot-pounds. Now that we have that, we bring into this equation right here, and this is the M of N we just calculated. F of Y was given, and we need to figure out the plastic section modulus. So we want to get Z of X, so we have to divide our M of N by F of Y. Make sure that you are using apples to apples, so get the units right. F of Y is in inches, Z of X is inches. The moment right here is going to be in foot-pounds most likely, so you're going to multiply by 12, and we get a Z of X of 17.3 inches cubed. Now, once we have this, we can go to that website and figure out the smallest member that has a plastic section modulus of at least 17.7 inches cubed in the X direction. Just showing you how things cancel. So here's a snippet of it, but let's actually go there. Let's do it a little bit longer process. So it was 17.7, and then for that it's properties. Make sure you're in the properties tab. And well, look how much this can handle. A 44 by 335 pounds, meaning 1 foot of this beam weighs 335 pounds. So we're way lower. Let's keep going. It was 17.7. And the way they're done is a little bit weird. They group it by section. So all the W14s, and then it goes from the heaviest W14 to the lightest W14. And then the W12s, the heaviest W12 to the lightest W12. All right, so we were at 17.7. So right here, I see a W10 by 17 works, and that's the lightest W10 that I would use. So I don't even need to consider all these ones yet, unless for some reason it didn't work for deflection. I'm also going to check the W12. So W12, what's the lightest W12 that works? 17.4, ooh, that's actually too small. I need at least 17.7. So W12 by 16 also works. And W12 by 16 is actually lighter than a W10 by 17 because 16 is less than 17. Also, a W12 by 16 is actually stronger. So a W12 by 16 has a section modulus of 20.1 as compared to 18.7. So this right here is lighter and stronger. I'm going to choose this one. Let's look at W14s just to make sure. And the W14s, well, the lightest W14 is 14 by 22, which is already more than the 12 by 16. So I know for confidence that this 12 by 16 is the lightest member that can support the bending moment. So I'm going to choose W12 by 16. And this is just showing you the same thing. Again, W10 by 17 works, but a 12 by 16 weighs less because it's the second number that dictates how much it'll cost, not the first number. So now that I have the member, we're done with bending moment. Now we're going to go to shear. So we're going to take our max shear from the diagram. I forget what it was. Oh, there it is. 9,800 or 9,810, and we're going to multiply it by the shear factor of safety, which is 1.5. Gives us 14,715. And now we're going to check the strength of that W12 by 16 member to make sure that that shear strength is greater than this applied shear. So the equation for that is 0.6 multiplied by the yield stress multiplied by the area of the web. Area of the web was dictated by the depth multiplied by the thickness of the web. So for a W12 by 16, the depth is 11.99. The thickness of the web is 0.22. So 0.6 times 50,000 psi times 12 times 0.22 gives us 79,134 pounds. So this is how much shear that this beam could handle. We're only applying 14,000 pounds of shear. We're not even close. This is what I mean when I say it's probably not going to fail from shear. We're not even close to what it can handle. If you want to see where we get these numbers from using the website, you won't find it here, right? This is the weight per pound. No, I'll let the inertia, no, come and play later. We actually have to go to the top and go to dimensions. And it's frustrating because it goes to the top, so you have to scroll all the way down to the W12 by 16 again. W12 by 16, and here's where you see the depth and the area of the web. Okay, let's keep moving. Now we have to check deflection. So we're going to do L divided by 240 for live and dead, and then L over 360 for just live. So take our length, which is 18 feet. Don't forget to multiply it by 12 to get into inches. And then 18 multiplied by 12 divided by 240 is 0.9 inches. We're allowed to deflect 0.9 inches from the total load, and then L over 360 gives us 0.6, so we're allowed to deflect 0.6 inches from just the live load portion of the total load on top of the beam. Now let's check what we actually have. That's what's allowed right here. What we actually have is from this equation right here, which will be given in the beam shortcut worksheet, L to the fourth divided by 384 EI. W is the pounds per linear foot. L is the length of the beam in inches. E is the modulus of elasticity in PSI. And I is the inertia measured in inches to the fourth, which you get from that the website. So let's go back to the website real quick. We're looking for inertia for a W12 by 16. Okay, so we got to go to properties again, and then W12 by 16 is way down here. W12 by 16 gives me a I value of 103. I don't want the one for the y-axis. I want it around the x-axis, so 103. So let's go back. And that was shown right here, but I just want to show you how to get it yourself. So I'm going to use the formula and realize that W is dead and live. So I'm going to add the dead and the live W's, which was 1,090 total. And this is, not easy to put into your calculator. But we have 5 times the W. Make sure that we're in inches. Notice how the W would be given in feet. And then the L, again, is in inches. Divided by 384. The modulus of elasticity for steel and PSI is 29 million, and then the I is 103. And plug and chug, have fun with that. Notice what cancels and what you're left with. We are actually left with inches divided by inches squared, or actually 1 over inches. This would come to the top, so it'd be inches squared divided by inches. We're left with just inches, and we get 0.86 inches of deflection. Really close for where we're just choosing this one from the bending moment. So that's actually good, right? We're allowed to bend 0.9 inches. We're actually deflecting 0.86. We're good. So now we just have to check the deflection from the live load portion alone. So we're going to do the same thing, only this time we're going to be doing the W as just the live load portion. Which, if we go back several slides, hopefully this doesn't take too long. The live load was 790 PLF and the dead load was 300. Add them together is where we got the 1090. The live load portion by itself is a 790. Let's go back to where we were at. Okay, so then W is the 790, same thing, and now we're checking it as compared to the L over 360, and it does not work. We have an allowable of 0.6 inches, but we're actually deflecting it 0.63. Ugh, so what do you do when it doesn't work? You cry. That's the first thing that you should do every time is cry, because all that work is wasted. No, not really. We try again with a larger beam. We know a 12 by 16 works for bending. Let's try a different one. Now you could just choose the next size up and check that one as well. There's actually a more methodic way to be sure that you know it. You can now look at it. So we know that the equation is 5W L to the fourth over 384 EI. What is changing when you choose a different member? Well, the loading's not going to change. That's the same. The length of the beam is not going to change. That's still going to be 18 feet. The E is not going to change. That's just based on the steel. The only thing that will change is the inertia. And a heavier beam will have a larger inertia. And notice how W, L, 384, 5, and E are all going to be the same. So we can actually figure out what our required inertia is. And we'll do a ratio. So we're going to do the actual deflection divided by the allowable deflection and set that equal to the required I, this is what we're looking for, divided by the original I that we used. So we had 0.63, the allowed was 0.6, and then we're going to multiply that by the original, and that gives us the required minimum inertia that we need. So now we're going to go back to the website, and we know that we need at least 108. So now we're going to choose the lightest member that can handle 108, or that has 108 inertia. So 12 by 19, that works. Let's check the 10 and the 14 also. You always want to check the nearest ones. So W10 So W10 by 19 does not work. That's lower than the 108 that we need. And then the W14s, nope, the lightest W14 is 22 pounds per linear foot. So the next one is W12 by 19 that we're going to choose. That has a inertia greater than what we need. So let's go back. I'm going to choose a W12 by 19, which has these properties. And we can check the deflection if we want, but we know it'll work. And we know that because it works, because the smaller member worked for bending and shear, the larger one will work as well. So by inspection, the plastic section modulus and web area are larger for the W12 by 19 than the W12 by 16, and therefore we are sufficient to say that the bending moment and shear will work. There is no need to check for moment and shear. Therefore, a 12 by 19 beam will work to support that load. Final answer. This is the size beam that an engineer would say to use given that loading scenario. Okay, hopefully that made sense. This was a very comprehensive example. And next, or week 2, marking period 4, I will be expecting you guys to do these types of problems on your own.